Good day, everybody. Today I want to look at Jacobi elliptic functions. So I'll go to this Wolfram Math World website for the standard definition. Of course, you can find them all over the place on the web. But basically, if you just want a quick definition, we have this value u, which is given by an integral, and u will depend on, we like to use phi, so u will depend on phi and k, and it'll be this integral from 0 to phi, 1 over square root of 1 minus k squared, sine squared of t dt. And of course, this t can be any dummy variable. Sometimes you'll see a theta there, among other variables, but I like t. So u is in terms of this integral, which we can't in general evaluate for most values of k. We can when k equals 1. We'll get to that later. Or k equals 0. So u depends on phi, as I'll emphasize more graphically in a bit. Also, phi then depends on u. There is a one-to-one relationship. So if each value of phi gives a value of u, conversely, each value of u will give a value of phi. So we can think of phi depending on u. It's called the Jacobi amplitude. So phi is some function of u and k. And then sun u, which also depends on k, but snu is going to be the sine of that amplitude, Jacobi amplitude, which is sine of phi. And similarly, kun u, cnu will be cosine of phi, and dun u, dnu will be this quantity. It's also can be thought of as d phi du, which is 1 over du d phi. That'll give this same value right here. So again, I rewrote this definition for u in terms of phi, so we have that. And then in most of the graphs we will later see, but I put it right here, that there's a quarter period that we call capital K, nice and confusing, but that'll be the integral from 0 to pi over 2 of this same integrand. And so most of the graphs I look at, I have little k 0.8, which leads to the quarter period, capital K, being just about 2. So again, we can graph u in terms of phi. That would be easy to do as a standard function. You just graph this integral. But I kind of wrote it parametrically for what's going to follow. So another way to do it is we want the horizontal axis to be phi, and then the vertical axis is u of phi, which is this integral. So that's how you can graph u in terms of phi, just from the definition. That one's super easy. But if I want to graph phi in terms of u, then parametrically all I have to do is switch the x and y there. So now I'll have the horizontal axis be u, and then the vertical axis be phi. So that's now gives me the graph of the Jacobi amplitude, or phi in terms of u. So there's the graph. So as we saw, Cn of u is defined by kun u is cosine of phi of u. So to graph that, then I'll graph y will be cosine of phi, and that's the vertical axis, and the horizontal axis will be u of phi. I need the horizontal axis to be u if I want to graph Cn of u. Right? So for y equals Cn of u, to graph that, the horizontal axis has to be u, so that's what we'll do parametrically. The vertical axis is then cosine of phi. Similarly, if I want to graph sun u, which is sine of phi, just have the horizontal axis be u, and then y will be sine of phi. And of course, to graph dun u, just have the horizontal axis be u, then y will be this quantity, square root of 1 minus k squared sine squared phi. So there's the graph. Just for emphasis, I'll do it on the graphing calculator. So notice the parameter of phi can be any variable, really. except on the graphing calculator, it's forced to be, the parameter is capital T. So I rewrote it this way. So we'll graph it using capital T as our parameter for graphing. And then the integral, the dummy variable of integration can be anything as long as it's not the same upper limit. So I wrote it as V for Kunyu or W for Sunyu. So this is the same thing right here, but just instead of phi for the upper limit and sine of phi, I have capital T. And then for the variable of integration, it could be anything that's not capital T. So of course I can graph U in terms of phi on the graphing calculator, but I won't do that. And I can graph phi in terms of U. In other words, I can graph the Jacobi amplitude, but I won't do that either. And of course we can graph Kunyu and Sunyu is the one I'll graph. So here we are. Look at what I've typed in already. So I've got the integral 0 to capital T. That's what I have to use. There's my integrand. Here I use U as the dummy variable. I didn't want to put that on the paper because then we use U for the U in terms of phi for defining Kunyu and so forth. So I thought that wouldn't look good, but I don't know, for whatever reason I use U as the dummy variable of integration here. So that's that. So let's look at the graph then. So simple as that. To graph y equals Sunyu, I just need the horizontal axis U in terms of phi, and then y sine of phi, or capital T. So graph. It starts pretty quickly at first, but does slow down quite a bit as it moves along and calculates. So here I have the graph over 5 quarter periods, or 5 quarter periods. So, and each tick marks 2, which is roughly what the quarter period is. So look here. So there's 2, 4, 6, 8, and that's 1 full period. And then here's 10, which would be 5 quarter periods. So there you have it. So a little deeper look at the graphs. First, here's my integrand over a quarter period when k is 0.8. And so if you integrate, you get the u in terms of phi, right? So there's the integrand, and u is defined as that integral. You can see it right there. So u is the integral from 0 to phi, 1 over square root of 1 minus k squared, where k is 0.8 right now, sine squared t dt. And we can kind of see, so if I integrate from 0 to pi over 2, I'll get the same area under the curve if I then go from pi over 2 to pi. But anyway, so this is u in terms of phi from 0 to pi. And just to beat it to death, I'll go 0 to 2 pi. So here's a look at it. So there's the integrand. Of course, it's pi periodic, but the area under the curve from 0 to pi over 2 is the same as the area under the curve from pi over 2 to pi. And then after that, of course, it just repeats anyway. So again, as stated, if we get u in terms of phi, then I can get phi in terms of u. Like here I did it numerically. Pick a value for u, and in here it solves numerically for the value of phi to get that value of u. So again, just a basic idea. Since u in terms of phi is 1 to 1, it's invertible. Now just to look at what happens for different values of k. So the previous was all at k equals 0.8. If k equals 0, then the integrand is actually 1. And so then u equals phi. And that's what I see graphed right here, u equals phi. As k approaches 1, what we're going to approach is the arc cosine of 1 over cos u, which is secant, hyperbolic secant of u. And I have that graphed as well. So on the vertical axis, I've got phi. On the horizontal axis, I have u. We didn't label them, but u is on the horizontal here. Phi is on the vertical. So as k increases, not too much change. So we'll see that happens a lot. Things don't really start happening until around 0.8, but so here we are. There's my 0.8. But if I keep going, you can see it is approaching that hyperbolic. Well, it's the arc cosine of 1 over cos u. If that was too quick, I do have a slower version. So again, there's the definition of u, but I'm graphing the inverse, which is easy enough to do just parametrically. X is u, y is phi. So here I start at 0.99, just to go a little slower. Get the idea. We'll see it on paper at some point. And then as stated, to get y equals CNU graphed, just parametrically. So x is u of phi, y equals cosine phi, graphs CNU. So here's a look at CNU. It's actually, it's distorted, but this is the graph of cosine, the regular cosine curve. You could say u is the horizontal axis, so this is just cosine u when k is 0. But as k increases, it's kind of a slide, and then one thing I noticed, we start getting changes of concavity, which might be interesting. But we approach the hyperbolic secant of u. That's in blue, 1 over cos u. That's what we approach. Here it is for k equals 0.99. Yep, happened pretty quick there. If we want to think about the points of concavity, here it is for k equals 0.96. So I've labeled them, and you can kind of tell. You've got changes of concavity at those points. So right now we're concave up. We also switch at the axis, so we're concave up. Now we switch to concave down, and we stay concave down until we get to that other inflection point. So I stay concave down. Now I switch back to concave up. Concave up. Now switch to concave down. And so stay concave down till you hit the u axis, and switch back up. So how interesting is that? The points of concavity start appearing when k equals root 2 over 2, the square root of 1/2. So if I type in this decimal approximation of square root of 2 over 2, square root of 1/2, it is rounded up. That 812 was rounded up. So if you had more decimals, it would be 811. I forget what comes after that one, but something bigger than 5. So it rounds to 2. So I'm slightly above root 2 over 2. And so these points of inflection occur here at this x and y. So y is roughly 0. It's really, really close to the axis. So the points of the new points of concavity start at the axis, and then they come outwards. They come outwards pretty quickly. So let me just go to say 0.7072. So maybe not too quickly, but so that's where the points of concavity occur. 0.71. Start to separate out 0.81. And they've gone most of the way they're going to go. They don't keep going away. They have a limit. This point heads towards the limit of the point of inflection of y equals hyperbolic secant u, which I guess might make sense. Also, if I do a point below root 2 over 2, or a value of k, below root 2 over 2, then I'm not getting any points on the graph. You're not getting, if you solve, it's a complex number. So we'll see what happens. So unable to plot those points, they were all complex values. Anyway, so here's the graph of soon u, horizontal axis u, vertical axis sine phi. So u of phi, sine of phi. If you want to look at the graph for different values of k, when k is 0, it's actually just regular sine u. But then as k gets bigger, oops, gets distorted. And if we're interested, it's going to approach hyperbolic tangent of u. And here's dnu, dnu for k equals 0. dnu is 1. That's easy to see from the definition. When k is 0, it's easy to see we get cosine, sine, and then 1. But for other values of k, it looks like this. Oops. And it heads towards hyperbolic secant of u, just like CNU did. All right, so that was a look at the graphs. Back to some of the things I mentioned. If I re-look at the definition, so since u depends on phi and it's 1-to-1, we can think of it as also phi depends on u, the amplitude of u. And then kun u is cosine phi, cosine of the amplitude u. Soon u, sine of phi, dun u. d phi du, which is 1 over du d phi, will give me this by the fundamental theorem of calculus. And then now, so some properties. Yeah, I haven't done the properties yet. So kun squared plus soon squared, well, that's just cosine squared phi plus sine squared phi. And dun squared is 1 minus sine squared, 1 minus k squared, soon squared. So that should be easy to see. In fact, I have that right here as well. So same thing I just said, but now typed up. So again, properties, kun squared plus soon squared is cosine squared plus sine squared, so that has to be 1. Dun squared is square root of 1 minus, or dun is 1 minus, square root of 1 minus k squared, sine squared. So dun squared is 1 minus k squared, sine squared. All right, so I just said look at the derivatives this way first. So you can take d du of soon u will be d du of sine of phi of u, but the derivative of sine is cosine, and then the derivative of the argument is the definition of dun u. So the derivative of soon u is kun u dun u, because cosine phi is kun u. So that's easy, and the others are easy too. Derivative of kun u would be derivative of cosine phi, but the derivative of cosine phi is negative sine phi, and then times the derivative of the argument is dun u. So we get that. And depending on how you want to define dun u, you can define it as this square root or get it from the property, but either way. Then the derivative of dun u, if you take the derivative of this, it's to the 1/2 power, multiply by 1/2. The whole thing's to the negative 1/2, so it's in the denominator. Then times the derivative of what's inside will give you a 2, which will cancel the 2, but I've got a minus k squared, sine phi, cosine phi, derivative of phi. But the derivative of phi is dun u, which is this denominator anyway, so then they cancel and you're just left with that. So there's the derivatives. For concavity, I thought of another way to express the derivatives. Did soon first. Right. So if we want to graph y equals soon u, then I'll graph y equals phi, x equals u of phi. Right, so we did that. And then the derivative of soon u du is just dy du, which is the same as dy dx, because x is u. This is u of phi. So just do dy d phi over dx d phi by the chain rule. And then since y is sine phi, I'll get cosine phi, and dx d phi right here. So if you take the phi derivative of this by the fundamental theorem of calculus, it'll be just 1 over this square root. Plug the phi in for t. So it'll be that. And flip this up, and that's the definition of dun u. So You can get the derivatives this way as well. If I want the derivative of kun u, I mean, it's pretty much the same idea, but I want to get the points of inflection, so I kind of wanted to think of it, how I graph it. So if I graph y equals kun u, which is cosine phi, so this is how I'd graph it, and x would be u. Then the derivative is dy du, which is dy d phi over dx d phi, since x is u. And that'll be negative sine phi, dx d phi, easy to see. Flip it up, and you get that. And here I got dun u through the properties. But this allows me to get the second derivative. So the second derivative will be d squared y dx squared. And that'll be d dx of dy dx, which is d dy dx d phi over dx d phi. And so I have to take the derivative. Well, there it is. There's what we got before. And then dx d phi is that. So we'll go through too much there. But, use the product rule here. Get this. And if I flip this up, then I'll get a square here. And this will cancel. So flip this up and multiply through. And then simplify by factoring negative cosine phi out. Now I have two negatives here, so I still have one left over. And negative cosine phi here. So this is what I have. So I get this. So this is the second derivative. And then if I put it equal to 0, we get cosine phi equals 0. And that occurs at phi equals these values, which corresponds to these values of the quarter period, which is where it crosses the u-axis. Right, so that's a point of changing concavity. But we also get this could be 0, except if k is too small, you don't get a solution. Like if k is 1/2, I end up getting sine squared is 2. It's not until you reach 1, where once k is big enough so that this is less than or equal to 1, and that occurs at root 2 over 2. So we can find the values of phi in terms of k once k is in between these values, and so I can get my points of concavity. Lastly, so I put k equals 1 here. Notice if k equals 0, it's easy as well, and things are the circular trig functions. But when k is 1, I just get cosine squared here, so which means I get secant, and then the integral of secant we can do. We get this, and so I can simplify. Let's do it quickly here. But because I knew the answer, I kind of knew the direction to go. But so if u is this, then negative u, I just take the reciprocal, and notice if you add the two together, it gets this. And then if you get your common denominator, things simplify to this. So e to the u plus e to the negative u is this, but then if you factor out a 2, it ends up just being this. So then divide by 2, and that just becomes cos u is 1 over cosine phi. So cosine phi is 1 over cos u. This is when k equals 1. So that would be hyperbolic secant of u. So that's the kun of u when k is 1. And then from back to this equation, well, I guess take the reciprocal. Cos squared is 1 over cosine squared, or secant squared, and then cos squared is also 1 plus sinh squared. It's the identity of hyperbolic functions. So I can solve for hyperbolic sine, subtract 1, and this is then tangent phi, which means sine squared, which is tangent squared divided by secant squared, is hyperbolic sine squared divided by hyperbolic cosine squared, cosh, or tangent squared. And things are positive, so you can take the square roots, just keep the positive values. One other thing to note, so I mean, why does it happen? I mean, if you go to the quarter period will approach infinity as k goes to 1. Quite see it here, but if pi over 2, there's a vertical asymptote and go to infinity as phi goes to pi over 2 when k equals 1. But as long as you're below pi over 2, you can get values. All right, so I guess I'll finally wrap it up here for at least this video. I do want to get into, there's another popular way to define the Jacobi elliptic functions with a horizontal ellipse. So I'll look into that and compare the two. They have different integrands, so I'll have to resolve that problem. And then we'll also look at differential equations that the Jacobi elliptic functions solve, and in particular solving the pendulum differential equation. Might do that a couple different ways. So all right, yeah, I guess enough for this. So thanks if you were able to make it through, and hopefully you found it worthwhile. Also, I put a lot of documents in the description. Hopefully they will be beneficial to you as well. Thanks again, and have a good day.